All right, so we are back and we just have our very last lecture here of the semester, kind of wrapping things up a little bit and talking about a particularly interesting section of chemistry, which is something that doesn't get often discussed, which is green chemistry. So one thing to keep in mind about the practice of chemistry is that it can be very wasteful. And for example, just to give you an idea, like when you go into lab and you use the fume hood, which we used to use, of course, and I know you'll see them again. Those fume hoods use about the same amount of electricity as a single household does in a year. So that's an example of like practicing chemistry that can be very wasteful of energy or resources. Now, that said, I mean, that's not the hood's fault, and it's not that you shouldn't work in the hood. It's just that we need to be mindful of um, the consequences of our studies, basically. And when we do chemistry, we want to make sure that the chemistry that we do doesn't end up poisoning people down the line. Uh, and we want to make sure that we don't waste energy or we don't waste resources on a low yield synthesis when there's something that's more friendly to the environment on the other end. Chemistry nowadays has a pretty good like pretty good. I think people have a pretty good feel for that. But of course, like the history of chemistry is just littered with polluted sites. Like, I mean, just look up Teflon. Search Teflon's Wikipedia page and see how the perfluoric acid, how that's been treated as a chemical waste throughout history. So we're trying to get away from that. We're trying to do things that won't destroy this planet that we're living on. So green chemistry basically just refers to guiding principles of all aspects of chemistry, which is number one, we want to prevent the waste from our chemical reactions. So prevent it from even forming, not contain it or spill it or whatever. Number two, use less hazardous substances. That way, if there is waste that's generated, it's not hazardous waste. It can be reprocessed or recycled into something that's useful. Use safer solvents, ones that don't cause cancer, ones that don't cause fish kills, for example, stuff like that. And then also maximize what's called the atom economy. So think of atoms as like dollars, right? You want to be as efficient with the dollars that you have as possible. So that means that in your reaction, you want to use as few extraneous atoms as possible. So like, here's two examples of reaction. So this is Markovnikov addition of an alcohol, basically an OH group to an alkene. If you use oxymercuration, demercuration, we have all these waste materials. We have the boron is going to be a waste product. The mercuric acid is going to be a waste product, and the proton from the water molecule all are going to be wasted. They don't end up in your product. So that's an example of what we call poor atom economy. Not to mention that mercury too is a toxic material. So like starting by using this toxic material, that's no good. On the other hand, if you use acid catalyzed hydration, you have a catalytic amount of acid and water. Water is environmentally benign and that gets incorporated into the thing. So it's very good atom economy, and also you avoid the use of toxic substances like mercury 2 and boron. So yeah, so this is a pretty clear example of like good atom economy versus bad atom economy. Okay, so another few guiding principles that can help reaction be more green or more responsible. Use catalysts rather than stoichiometric reagents, because catalysts can be, they're going to go through a cycle basically and continue doing the reaction. You want to do energy efficiency, try to do reactions at room temperature rather than like adding heat into a reaction, or even cooling down a reaction as well can be difficult because in order to generate those cool temperatures, you use energy to do that. And then finally, try to find renewable feedstocks. So this is a relatively new thing as well. Basically, like don't use petroleum because petroleum is a limited resource and we're going to run out of it eventually. So if you can use basically things like ethanol or acetone, which can be generated from renewable resources, then you're in a much better position than using petroleum-based chemicals. Okay. So some final practical tips here. So this is just going to be like a few things here that are like things that can help you study, like tips for how you want to study. Um, and it's going to help you moving forward as well. Basically, when you learn reactions, you should organize them into two camps: reactions that alter the carbon skeleton, and then reactions that alter functional groups. Knowing that, then like having that in like an easy place to grab and like see, oh, I reduced the carbon skeleton. It must have been one of these reactions that did it. Or I added carbons onto the carbon skeleton. It must have been one of these reactions that did it. As you go into OChem 2, you're going to learn more and more of those. For now, we only know the two, right? We know ozonolysis to remove carbons, and we know alkylation of alkynes to add carbons to it. And then, so as you learn them next semester, you can add those reactions to the lists that you already have. So, and then a final kind of tip here is that to start syntheses is you can make your own synthesis problems. Basically, start from a simple reactant, and then choose a reaction, write out the reagents, and then predict what the structure of the product's going to be. Repeat that a couple times, and then go ahead and swap problems with a classmate. That's why we have the Pronto service or the chat service on Canvas. Just go ahead and like swap those problems, and then practice. Just give them the reactants and the products and say, hey, how do you get from the reactants to the products? That can be a fun way. I'll actually set up a discussion as well for that too. That's kind of a fun little method to do there. So like you can just start from an alkyne, let's say. So we start from an alkyne, you use your sodium amide that produces your nucleophilic carbanion. Then you use a methyl iodide that's going to methylate it on one side. So that gives you this methylated alkyne. Then you can do it again. You could use methyl iodide again. You could use, that gives you this interior alkyne here. And then if you use, let's say, hydrogen over Lindlar's catalyst, that gives you the cis alkene. So then you have your final answer, you have your starting material. And so this is what the problem looks like. Give that to a classmate and then compare your answers. So we'll go ahead and put that in the discussion. One thing that's really cool about this is that there's more than one way to solve a lot of different synthesis problems. So just keep that in mind, that like just because another student's answer differs from yours doesn't mean that it's not right. So yeah, so that's going to be a useful way to help you study. And there's a lot of these online to help you as well. And of course, we've got our PDF down below to help you with that. Okay, I mean, that does it for the semester. I can't believe it, but we're at the end of OChem 1. Thank you guys so much. It's been really a pleasure teaching you this semester. And please ask me questions, and we'll get ready for the final exam here. All right, I will talk to you soon. Bye-bye.